All right, so first things first, y'all had a couple questions about your homework. I just wanted to work those out real quick. So 27 was one of them. 27 was the integral from -1 to 1 of 2 minus the absolute value of x dx. So again, I want to graph this and see what this picture looks like. So let's think about our transformation, what's going on. Absolute value of x, of course, looks like 0, 0, 1. It's that line y equals x, but it's reflected over on this side also, so that's the absolute value. But because I have this negative in front, that negative is going to flip it, of course, over, and then I'm also going to shift up 2. So I've got a up 2 and a reflection. There's no shrinks or stretches here, so it's just going to be like this. This is down 1 over 1, so this would be the point 1, 1, 1. And then this would be 2, 0, -2, 0, 1, -1, 1. Okay, so I'm looking because I want from -1 to 1, right? So ignore that. Let me just redraw this for you. I'm up to 2. I am down 1 over 1. So I'm looking at, this is my graph, but my shape looks like this. So it kind of looks like a house there, right? So I see two parts here whenever I do this. I see a triangle and I see a rectangle. And so if I do the area of the triangle, of course, y'all know mine's not drawn to scale because, whew, um, area here, of course, is 1/2 base times height. And of course, the height looks like it's 1. Excuse me, and these points are 1, 1, 1, 1. So the height is 1, and the base stretches across 2, because 1 unit here and 1 unit there. So the area of this triangle would be 1/2 base, which is 2, times the height of 1. So the triangle up top has an area of 1 unit square, whatever that is. And then, of course, the area of this triangle on the bottom, this is 1 and 1, which would make this 2 across. So the length here is 2. The height, again, is 1. So this area would be 2 times 1, which is 2. And then I have to add those together. So the area here under this curve would be 3. So this is 3 units squared. Okay. And that is 27. Now, because I'm asked to find the integral and not the area, if this had been flipped over the axis, it would be negative. But because it's above the axis, it is, of course, positive. All right, let's look at 32. Let's see. Oh, 32 is a good one. All right, the integral from 0 to b of 4x dx. So this is where I really have to start generalizing, right? So let's graph the line first. We'll graph the function first, and then we'll. So I'm going to do, let's see, 0, 0, and then it's got a slope of 4. So 1, 2, 3, 4, and over 1. And so I've just got this line with a pretty steep slope. And I want to know from here, from 0, right, to any point, we'll call this point B. What is that area under the curve? Okay, so from any to any point B. So of course I've got a triangle here, and the area of a triangle again is 1/2 base times height. And B is going to fluctuate, right? It's going to be any particular value, or it's not going to be any particular value, but I want to write an equation that, depending on what B is, I could just kind of plug that value back in there. So here, if I'm thinking about, this is dropping down at 90 degrees, right? So this triangle, here's my base, and here's my height. So let's write it in terms of B. Now this point is going to be B, And then it goes up to, remember, this is y equals 4x. So I plug my x in there, right? So this point is b, 4b. So wherever I am, I take that value and multiply it by 4 to find the y coordinate there. So what that tells me is that this distance across here is b, and the height then would be 4b, right? So the area here would be 1/2 base times height. And now I can just clean this up a little bit. Half of 4 would be 2b squared. So this would be 2b squared. So I hope that answered your question about those. Okay, so moving on to some stuff, some a little bit of new stuff, and I know y'all hate it, and I'm sorry, but we must get through some new material. Um, I left you a list of integral rules yesterday, and then some problems where you had to apply those rules. Let me see if I can get to those. And so I know that you already did this for homework, but I did just want to touch on this just a little bit, a couple of things here. If your upper bound and your lower bound is the same, then of course the area is 0. There's nothing under there if the bounds are the same. Number 2 is a really important one because we do this often and we do this to help us evaluate certain integrals. But if you switch the bounds around, your lower and your upper bound, that just changes the sign that you'll get at the end when you evaluate that integral. For number 3, notice that you can split up different areas to get to, like if this one's going from A to B, you could split up. Think about this like a line addition postulate in geometry, or if C lies in between A and B, I can split these two up this way and then add them together. And that's sometimes helpful, and you've done that sometimes actually already as you split up areas, right? And you look, well, from -2 to 0 maybe is a semicircle, and maybe from 2 to 5 is a triangle. And so you do each one, then you add them together to find the total area. Same concept here. You can split those up. Number 4, anytime there's a constant, you can pull that out front, just like with derivatives. When we had that constant we pulled out front, you do the same with integrals. And number 5, really, really, really important. You can split these functions up with addition or subtraction, but you cannot do this if you are multiplying. So do not try. This does not work if this is multiplied or divided. It only works when you're adding or subtracting. Very important concept there. And so you had a few to work with, and I haven't asked you about the questions that you had just yet on those, but I asked you to tell me if you had any. So if you have any of those, let me know. That was your 1 through 6 that you had to do. I think that was, yeah, where you used what was given and you had to evaluate. So for instance, if I'm doing 1a, I'm going from 2 to 2 for g of x, right? And I have to use what's given in the first part here to evaluate. These is really just testing that you know the rules. So from 2 to 2, there's no area there. The area would be 0. From 5 to 1, all it's done is taking this integral and it's flip-flopped here your bounds, which means this integral would be -8 and so forth. So that's all that's doing there. So if y'all have any questions there, let me know. But I do want, and what I would normally do is I would have done this with what I'm fixing to tell you, but since I haven't been a little bit slower steps here so that we don't get overwhelmed. And I do apologize for not being there. It is beyond my control. Um, but when we evaluate definite integrals, okay, this is where we're going to go back to that concept of the antiderivative. Okay, so, and if you look, oh my goodness, I gave you that derivative sheet, and on the front side there were derivatives, and on the back side there are integrals there. That's going to be very, very handy for you. So keep that in mind. So remember we had some things where we said if we had like this function that was 2x to the 4th, right? To find the derivative, of course, we multiply and we subtract 1 from the exponent. But to go backwards with that, this is where we find the antiderivative. So this is where we do the big X, right? I wasn't sure I was recording. Um, this is where I add 1, and then I take that and divide by the front. So this would be 2/5 x to the 5th. And of course, if you did the derivative there, you'd end up back at 2x to the 4th. But I have to put that plus c here, right? And so this is what we call the antiderivative. And we did ones where if f of x was 1 over x, then the antiderivative of that, of course, would be the natural log of x plus my c, right? So that's kind of the concept that we're going to look at as we run through these. We're going to look at antiderivatives and then how we evaluate. So a couple of things. Talking about definite integrals. Now the difference in a definite integral and an indefinite integral is with a definite integral, I've got this upper and this lower bound, right? So I've got a restriction there, so to speak, for it. Indefinite integrals don't do that, but for right now, for definite integrals, I don't have to worry about this constant, and I'm fixing to show you why. Anytime I have if I want to find the integral of f of x from a to b, okay, what I'm going to do is I'm just going to find the antiderivative, and I'm going to evaluate that from a to b, okay? I mean, when I say evaluate from a to b, I'm literally just going to plug in f of b, like this is big F, remember, so this is antiderivative, minus the antiderivative evaluated at a, okay? And the reason you don't have to worry about that constant is because if I found here that the antiderivative, whatever that was, plus c, and this antiderivative, f of x plus c, whatever that is, right? If I subtracted them at a and b, well, the c's are just going to cancel and they're going to go away. So that was a terrible explanation. I apologize. I felt it as it came out and just, let me try that again. If this is true, right, and antiderivative plus c, so if this is f of b plus c, but then I have to subtract f of a plus c. Well, what's going to happen when I do that is that the c's are going to cancel. So what happens is I really don't have to worry about the c's here because I'm evaluating at specific points, okay? So for example, let's say I wanted to evaluate 2 over x plus 1 dx. Now you're going to have to remember, let's go from 1 to 4. You're going to have to remember those integral properties, okay, those rules that we talked about yesterday. This recording is not as patchy as what I feel like it is because I feel like I keep stopping and starting because things are happening. But anyway, as we look at those properties, one thing you always want to remember is when you see constants, pull those out if you can. All right, that's going to be an important property for you, and it's going to help you as you do your evaluating. Because as I look at this, I don't know the antiderivative of 2 over x plus 1. But now that I have 1 over x plus 1, I'm thinking, because this x is in the bottom, right? I can't really split this fraction up. This is looking like a log situation. And in fact, if f of x is 1 over x plus 4, maybe the antiderivative is the natural log of x plus 1. Would that work? And that's always what you want to go back and do is go, okay, well, would it work? So maybe I find the antiderivative. Well, now if I take the derivative, do I end back up here? And I do, because even when I chain rule this, right, the derivative is 1 over x plus 1, and the chain rule would just be the 1 there on the x. So that does work. So what I'm going to do is I'm going to say, okay, well, this is, remember that constant is sitting out front, the natural log of x plus 1. But what I'm going to do is I'm going to evaluate this from 1 to 4. Okay, and that 2 is sitting on the very outside there. So I've got 2, and I'm going to have the natural log, and you start with the b. So this would be 4 plus 1 minus the natural log of 1 plus 1. So I get 2 times log 5 minus log 2, right? Now, if you recall your log properties, and I know y'all hate those so much, but when I am subtracting, if I want to condense that down, then what I want to do is I want to divide those two values. So this is really 2 times the log of 5 halves. Now, keep in mind, while you might not have to do that on an FR2 situation, if you're in a multiple choice type situation, they're definitely going to have it simplified down like that for you to ensure you know those log properties and you can apply them properly. These, you may find that you have to look at those, especially the trig identity ones and stuff. Make sure you go back and look at that. Let's see some examples here of some evaluation. Maybe I can do another one with you. All right, so this is going to be like 19 through 30 is what we're going to do. Let's just do an easy one. Let's do number 21. And again, remember, some of these you might have to look up on your sheet to see kind of what they look like, right? All right, but this one is from 0 to 1, e to the x dx. And this is a super easy one because, of course, we know that if f of x is e to the x, then the antiderivative is e to the x. The derivative is e to the x. In fact, e to the x is one of the easy ones here. So what we're going to do is we're going to say, okay, well, to find this, then we're going to do e to the x evaluated from 0 to 1. So e to the first minus e to the 0. E to the first is, of course, 0, minus e to the 0 is 1, so we get negative 1. So that's just kind of a brief overview there. I will talk tomorrow about the mean value of the function, but for right now, I want you to try some of these using the antiderivatives, at least 19 through 30 there. You'll work together and talk about it and see what you can come up with. So that's what, 1, 2, 3, 4, 5, 6. So 12 problems. And of course, remember, look some of these up on your sheet to see what those are, okay? And let me know if you have questions.